right? I thought there'd be data. Is anyone out there?
Welcome back. How is the homework going? At this point, I usually say, well, I insist you see this, but I don't think there's anything I really need to do to clarify this one. I just wanted to say that in problem 1 on the homework, you have, I think, a normal distribution, and you're testing the null hypothesis that mu is some fixed mu naught versus the alternate hypothesis that mu is not mu naught. And I think it doesn't say, but if I were you, I'd base the test on X bar because it's the mean of a normal distribution versus the sample mean. So, step 1 is going to be to pick a statistic, and X bar, definitely the way to go. Statistic. Okay, but step 2, the form of the test. This is going to be like, how does the alternative hypothesis being true get reflected with that statistic? And so you want to reject this null hypothesis in favor of this alternative if X bar is significantly higher than mu naught or significantly lower. So it could be reject the null hypothesis in favor of the alternative if X bar is greater than some, well, there's actually 2 points I want to make here. So greater than some C or, less than some D. The first point I want to make is that this is going to be hard to do because we really want to think, I mean, we could do it this way, but you really want to think of it in terms of not just high, but higher above mu naught. So I would make this like mu naught plus a C and some mu naught minus a C, a D. That was my next point. My next point is there would be 2 unknowns to solve for. And so why don't you just make them the same? We can find a C such that we're going to reject if X bar is greater than mu naught plus C or X naught is less than mu naught minus C. So in theory, they could be different, C and D. So 2 things I wanted to point out. One is that I wouldn't just go with above a C and below a D. I would phrase it in terms of mu naught. And the other is I would not have a C and a separate D. And there's only one thing to solve for. And there's lots of nice symmetry. So we're talking about maximum likelihood estimators, or MLEs. And we did some examples last time. And I have a couple of special cases for you today. So the first is when you have 2 or more parameters. So this is a 2-parameter example. And we started at the end last time. I said I wanted to do the normal distribution with both parameters unknown. So both mu and sigma squared unknown. And we want to find MLEs for mu and sigma squared. So you would approach this just like you do all the others. You would write down, so the PDF for any one of these is an f of x and parameter mu and sigma squared. And this is 1 over the square root of 2 pi sigma squared e to the minus blah, 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 blah. So it looks like that, and there's no indicator here because it takes on values from minus infinity to infinity. And so from this, we can make the joint PDF. So this is f of a vector, mu and sigma squared. And because things are IID, we just need to multiply these guys together. Okay, so you just go and you put your xi's in here and multiply them all together, and you will get, so this is a common way to write this. Obviously, you have 2 pi to the 1/2 in the denominator, and that gets repeated n times. And if it's in the denominator, we can write it as 2 pi to the negative n over 2. I think this is a lot nicer. So you don't have to write the first part this way, but I would say 2 pi sigma squared to the minus n over 2. And then for the rest, because I don't know if I want to deal with the exponent or not. I mean, you can certainly use exp, so you don't have to write exponents. Guess I won't, but we'll have e to the minus 1 over 2 sigma squared, the sum as I goes from 1 to n of xi minus mu squared. Okay, so the next step in maximum likelihood estimation is to come up with a likelihood. And this is where you get to drop multiplicative constants of proportionality. So you could, this is not necessary, but you could break this into like 2 pi to the minus n over 2 and sigma squared to the minus n over 2. And then this would be a constant that could be dropped for the likelihood. But it's going to go away anyway. So I don't know if you want to drop it or not. I guess I'll just leave it. Let me just, I'm not actually going to factor it this way, but if I did factor it this way and then I took the log of everything, the log likelihood, I would get the log of the 2 pi to the minus n over 2 plus, well, actually, if I took the log of everything here, I'd get minus n over 2 log of 2 pi minus n over 2 log of sigma squared. And when you take the derivative with respect to mu or sigma squared, this term is going to zero out. So that's where every constant would have gone. But I'll just leave it because it's kind of maybe more work to take it out by factoring that. I don't know. Okay, so the likelihood, we're calling these capital L. These are a function of the parameter or parameters, so mu and sigma squared. And I'm just going to take this to be, in this case, the whole thing. Okay, next step is, usually take the log of this. Our goal is just to maximize this with respect to both parameters, and that doesn't necessarily mean you have to take the log, but it's almost always a good idea. And I let you know last time that you're going to get so used to it that one day it's not going to be a good idea. You're going to make the problem worse. So just keep in mind that taking the log is not a requirement. Okay, so next up, the log likelihood. So I've been calling this like a lowercase script L. And this is the log of the likelihood. And if you take the log across here, you'll get negative n over 2 log 2 pi sigma squared, and then minus 1 over 2 sigma squared, sum of the xi minus mu squared. So everything's the same as what we did before, but at this point, because we have two parameters, we want to maximize it with respect to both parameters. So it's two partial derivatives here. I'm going to take the derivative with respect to mu of the log likelihood. And the first term just goes away. There's no mu there. And the second term, I can bring the derivative through and inside the sum, and I will get in that, for that term, I'll get 2xi minus mu to the 1 times minus 1, little chain rule action. And doing that on all the terms, I'm going to get positive 1 over 2 sigma squared times 2 times the sum as I goes from 1 to n of xi minus mu. So I just brought the derivative into the sum and took the derivative of each of those guys. Okay, so blah, 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 blah. Lots of blahs today. Okay, you want to set this equal to 0. And we still have to take the other derivative. And in general, if you have two unknown parameters or even 3 or more, you're going to have 2 or 3 or more partial derivatives, and you want to solve the system simultaneously. It's just that in this case, we actually can solve for mu. So this is going to be 0. This is going to imply that the sum is going to be 0. Right? That the 1 over sigma squared is not going to make this 0. And so this is saying that the sum from 1 to n of the xi minus n mu is 0, and we can solve for mu and put a hat on it, and that is that mu is x bar. So in general, you should expect to have to use both equations to find the parameters. But in this case, we got the MLE. Yeah, we should check that we didn't minimize anything, but let's do the other derivative. So the derivative with respect to sigma squared, we're going to talk today about how the MLE for sigma is going to relate to the MLE for sigma squared. But at this point, it's just a parameter. So you should maybe think of it as a symbol, like not as something squared.
Can I ask a quick question?
Yeah.
So you've mentioned a couple of times that we should be checking that we're not minimizing anything, and that makes sense. But I mean, is it possible that we will, like, we won't have a maximizer, or that we'll have to like look at the endpoints of the distribution or something, or
That's
what?
my next example, actually.
Oh, okay.
Yeah.
Cool. Well, then
Thanks.
never mind.
Hey, so I also just want to reiterate that I don't need you to check in here. Just know that if you go out there and use this in another class or in your research, maybe you should check, because it's a pretty pathological example where you're not going to find the maximum by just taking the derivatives and setting it equal to 0. So, all right, looking at my likelihood, I'm going to take the derivative of this guy with respect to sigma squared. So I've got minus n over 2. The derivative of the 2 pi sigma squared with respect to sigma squared is 2 pi over the thing itself. That's the derivative of the log. You can see the 2 pi's canceling, so it doesn't matter that if we didn't have them there to begin with. And then the other term had a minus 1 over 2 sigma squared in front of some stuff. And if you think of that as sigma squared to the minus 1 and take the derivative, where you'll get minus sigma squared to the minus 2, then the rest of this derivative of the log likelihood becomes becomes positive 1 over 2 sigma squared times the sum xi minus mu squared. Let me know if you want me to go through any of those moves in slower motion. I'm happy to do so. Oh, yeah, I have to remind you. I don't have to remind you. I want to remind you. This week's colloquium is it's another really important guy. So I got together 3 famous people for this semester. The first was Percy on the first week, and the next is this guy. And I wasn't able to advertise it because he was being shifty for 3 months. And Sunday night, I was like, "Are you doing this or not?" You know, and I finally got a commitment. So I didn't want to advertise and have to cancel and have any awkwardness. But now I'm worried about getting an audience together. So if you want to come, come. I'm not making you come, of course. And his abstract maybe won't look interesting to you. It doesn't look interesting to me, but he gives amazing talks, and it's like he's really great to listen to. So, okay. All right, so set this equal to 0. And we've got, let me clean this up a little bit. I get rid of the 2 pi's. I can, sorry, let me just rewrite this. Guess I can get rid of the, not important. There's no reason for me to write this line. Just trying to clean this up a little bit. Okay, so I don't have to combine these and get a common denominator because I don't care about the expression on the left-hand side, just solving for the sigma squared that makes this equal to 0. So my advice is usually, for most problems in probability, to multiply through by the common denominator. 2 sigma squared on both sides. And then what's left on the left side is minus n sigma squared plus the sum of the xi minus mu squared, and then the right side is still 0. So if you solve for sigma squared, I'm going to keep this still lowercase, then it's going to be the sum of the xi minus mu squared over n. But of course, you can't use mu in your estimator of sigma squared because you don't know mu. Remember, we're solving the 2 partial derivatives simultaneously, so we need to plug in our estimator mu hat here. throw a hat on it, make things capital. We are done. This is the sum from 1 to n of xi minus mu, minus x bar squared over n. Again, it's biased. This is the biased definition of sample variance. You know, if we had an n minus 1 in the denominator, that's what we've been taking to be our sample variance. So again, biased, which does not bode well for me trying to push these over the idea of method of moments estimators. But we're going to start getting to the good properties. For example, they are all guaranteed to be asymptotically unbiased under a minor restriction. Okay, so yeah, let me just pull it together. I've got mu hat is x bar, and this calls for cut and paste. And the sigma squared. So we're done with this example. Any questions? All right, so the next example, which was just requested anyway, but is an example where the parameter is in the indicator. So this could be like you have x1 through xn, a random sample from the uniform 0 theta distribution, and you want the MLE for theta. But I'm going to kick it up a notch and use a slightly more complicated example. I'm going to have the parameter in the indicator and 2 parameters. So suppose that x1 through xn is a random sample from the distribution with the following PDF. So this does, I'm going to say it does not have a name, but I guess you can think of it as some sort of like shifted, I don't know if this has a name. It's not certainly not a common distribution, but maybe we can match it up to something on the table. I don't know. A random sample from the distribution with the following PDF. So it's going to be a function of x and a parameter theta and a parameter lambda. And it is theta lambda to the theta x to the minus lambda minus 1 on lambda to infinity for x. And the parameter space here is that both theta and lambda is greater than 0.
Question.
Yeah.
You said x to the minus lambda, but you wrote a theta. So
Oh, that's right. Yeah, I do want it to be minus theta. Thank you. So this is the correct exponent, but my words were not correct that I spoke. Okay. Okay, random sample, that means IID. So the joint PDF, f of the vector. You know, just like our definition of the size or level of significance of a hypothesis test should really be a supremum instead of a maximum, this too should also be a supremum. All the maximizing we're doing here. So if the maximum occurs, well, I'll show you. Let's go. Okay, so if you multiply this out, because these guys are IID, you get to multiply individual PDFs together. And I'm just going to cut to the chase here and write down the simplified thing. I've got theta to the n, lambda to the n theta, and I have a product of xi, each raised to the minus theta minus 1, but that's the same as taking the product and raising it to the minus theta minus 1, which is going to be a little easier in the end. So that comes from the product of each xi raised to that power. And then a product indicators. I probably wouldn't even get this far in writing this, because my advice to you is gonna be it is if the parameter is in the indicator to just make a note of it, kind of a marginal note, and leave out the indicator, because we're going to go forward and take the log of this. And we talked last time about how you don't take the log of an indicator and you don't take the derivative of an indicator. It just like comes along for the ride and is telling you what part of the space you're in. So I could rewrite this indicator as this is saying that I've got some lambda and all of the x's are above lambda. And that's equivalent to saying the minimum x is above the lambda. So I can get rid of that product. But my point is that you should just kind of ignore it, but keep it in mind. It's going to be important for our maximization, but not something you're going to take a log or derivative of. Okay, so likelihood here. If you wanted, you could break this up into this product of the xi to the minus theta, and then a product of the xi to the minus 1. And you can drop this whole thing because it's a constant with respect to thinking about this as a function of the lambda and the theta. So the x's are fixed in maximum likelihood estimation. You observe them, and then you're trying to find the parameters that make them most likely. So a likelihood. This is going to be an L of theta and lambda. And I'm going to take theta to the n, lambda to the n theta, the product as I goes from 1 to n of the xi. And I could just have minus theta there because I'd be dropping that constant with respect to the parameters. But I'm going to put it in again so we can see that it disappears so you can feel better about dropping future constants. Okay, the log likelihood. We're calling this curly L, theta, and lambda. This is n log theta plus n theta log lambda minus like theta plus 1 altogether, and then the log of that product, which you can leave as the log of a product, but in stats, it's just always nicer to have sums of things rather than products of things. Now, there's nothing wrong with leaving a product in your answer here, but I moved it in to a sum. Okay, so I'm going to take the derivative with respect to theta, and I get n over theta from that first term, and I get n log lambda from the second term, and I get the negative of the sum as I goes from 1 to n of the log of the xi. Because, and I'll stop doing this kind of slow motion move after this example, but this is negative theta to the sum of the logs minus another sum of the logs. And with respect to theta, that would disappear in the derivative, which is why we didn't need it in the first place, which is why we could have left this off. Okay, so I'm gonna set that equal to 0. And two unknowns there, right? And I don't think I can, like we did in the other example, solve for one until I write down the other partial derivative. So going back up here, if we take the derivative with respect to lambda, there is no lambda in the first term and no lambda in the last term. So the only thing we get is n theta over lambda when we take the derivative of the natural log of lambda. And so I'm going to set this equal to 0. And then, warning, warning, made me think of Danger, Will Robinson. Danger, Will Robinson. This cannot be 0 because n is a sample size. Yeah. Yeah, that robot followed that boy around and made sure his derivatives were okay. Yeah, so this can't be 0, right? N is a sample size, that's not 0. Theta was given to be greater than 0. The denominator can't make this 0. So it's kind of that this derivative gives no information. And this always happens. I don't know if I can guarantee, I don't know if I can guarantee it, but this 99.999% of the time, this is going to happen when the parameter was in the indicator. So this derivative gives no information. And so we're not, stuck. We still have the goal of maximizing the likelihood. And the parameter that gave us trouble is the lambda. But so now I would look at the likelihood, because what's happening here is, I don't know if it was Cooper before, I just heard the voice, but someone was asking about not having a maximum in the right space. So at this point, you would just observe the likelihood and look at this parameter that caused problems, and here it is. And so because of how the likelihood is a function of this parameter, you can see that the likelihood is an increasing function of lambda. And we do have some endpoints here because, go back to my picture here, those dots were the sample, the x1 through xn. Given that you've observed those data points, what is the largest lambda could possibly be? So you, oh, with a laser, and I should have kept it. Let me write that down here. So when you have this problem, you note that the likelihood is an increasing or maybe decreasing, in another case, function of lambda. And if you're trying to maximize the likelihood, that you want to take the largest lambda in this case. So want lambda largest. And this is where the indicators come in. The indicators, whether or not you simplified it to a minimum, says that all of the x's have to be above lambda. And so given that you have this fixed data, what is the largest lambda can be? So you start like inching it up here, and the highest you could go is the minimum value for the x's. So the MLE is going to be the minimum of the x's because the smallest x corresponds to the largest possible lambda. Because all the x's have to be above lambda, and those are fixed, and you're trying to figure out the largest lambda you can then have. Does that make sense? This is going to happen every time a parameter is in the indicator. And I can't think of an example where when the parameter is in the indicator, you don't get one of your MLEs to be a minimum or maximum. Okay, so going back to the other derivative here, I'm going to plug in my minimum, my MLE for lambda, and solve for theta. That's really messy, and I copied a lot of other stuff. I'm going to erase it in a second. So I'm going to go back to n over theta plus n log minimum minus the sum of the log of the xi equals 0. And I'm going to solve for theta. And in the end, make sure everything's capital and random and put a hat on it. And this is going to be n over the sum of the log of the xi minus the log of the minimum. And just as a quick check, the minimum is among these guys. So if you're summing this up, one of these terms is equal to this term. So fortunately, the whole theta is coming out to be positive. Okay, any questions about that? All right, so here's an interesting property of MLEs that I think you're going to like going forward because it's going to make a lot of problems a lot easier. So suppose we're looking for the MLE not for a parameter, but for a function of the parameter. So MLEs for a function of the parameter, and our generic function is called tau. So tau of theta, which is our generic parameter. I.e. the MLE for some kind of tau of theta. Maybe I should spare you. I'm going to get started and not do this whole thing. So let's go back to our exponential example, which I think was our first continuous example here. So if we have x1 through xn IID exponential with rate lambda, then we have the MLE for lambda is 1 over x bar. We figured that out last time. And this isn't MLE. If it's not clear, I can put an MLE subscript on there. Okay, and this comes from the fact that the joint PDF looks like lambda to the n e to the minus lambda to the sum of the x's times a product of indicators that is not important if the parameter is not in there. So the likelihood is just this first part. And one thing you could do is reparameterize this in terms of tau. So I've got like a tau of lambda. Oh, I didn't tell you what the goal of this was. So let's find the MLE for lambda squared. And that's going to be my tau. So one way you can do this is you could just rewrite this likelihood and parameterize it in terms of tau. And for that, I would just kind of think of this a little more simply rather than looking like a function. I would say, okay, tau is lambda squared. So lambda is the square root of tau, especially given that these parameters are non-negative. We don't have any problems like that. And then you can rewrite the likelihood. It will look like tau to the n over 2 e to the minus tau to the 1/2 sum of the xi. So reparameterize in terms of tau. That is not simply this function with a tau plugged in. It's a new function, right? Because this one didn't have those 1/2s in it. So this is like an L tilde of tau. It's a new likelihood function. And then you would just do it. Like you would take the log of this and take the derivative and set it equal to 0. And what you'll find in the end is your MLE for tau is going to be 1 over x bar squared. And what we're seeing here, remember what this is actually short. This tau, the tau alone is short for tau of lambda. So here I'm saying the MLE for tau of lambda is 1 over x bar squared. And note that this is equal to 1, I'm sorry. This is equal to tau of the MLE for lambda. Because tau of lambda is lambda squared and the MLE is 1 over x bar. This thing being equal to this thing is always true for maximum likelihood estimators. And this is known as the invariance property of MLEs. And I'll give you a quick sketch of a proof. So for MLEs, the MLE for some function of a parameter is equal to the function of the MLE. And this is known as the invariance property. Of MLE. So it's going to make a lot of problems a lot easier.
That example, does tau happen to be like one increasing I'm still really skeptical. Are there some assumptions we have that make it about tau?
Yeah, we have to assume that tau we need d tau d theta to be non-zero. And so, okay, so the way you would show this, I'll put this in quotes because this is almost rigorous, but not quite, is that we have a likelihood that's a function of theta, and that is equivalent to, not the way I wrote this. Yeah, it is the way I wrote this. That's equivalent to a new likelihood that's a function of tau of theta. And so if you take the derivative of the left side with respect to theta, that's the same as taking the derivative of the right side. So we need tau, we need this to be true, and we need tau to be differentiable because we can chain rule this by saying this is the derivative with respect to tau of L tilde, tau of theta, and then the inside derivative of tau with respect to, write it this way, the derivative with respect to theta of tau of theta. And so I was going to say I do need tau differentiable for this, but all I can really say from this is I need tau differentiable for this proof. And in fact, I can prove to you that we don't need tau differentiable, but we do need this in order to make the last statement here. So the MLE theta hat plugged in all the way across here makes the left-hand side 0. This also depends on whether or not we have a unique MLE and there's no minimums or saddle points or weird things happening. So if you plug the MLE theta into the left-hand side, you get 0, and that's how we define the MLE basically if everything's nice. So all the way across, I mean, we'd have 0 is the derivative with respect to theta of the log of theta hat, and this is the derivative with respect to tau of L tilde, tau, and I'm plugging in theta hat, and then I have this other thing sitting over here, which, whatever, and then a thing, not a constant. I've got a derivative with respect to theta of tau of theta hat, but I'm assuming this is not 0. And so what we're seeing is that the thing that zeroes out the L tilde should be, by definition, tau hat, right? So to get the MLE for tau of theta, we're going to take the derivative with respect to tau of the likelihood and set it equal to 0, and we're going to solve for tau. So this implies that the derivative with respect to t of L tilde of tau theta hat, assuming it exists, assuming it's unique, this is going to be 0, assuming this derivative does not turn 0. And okay, so assuming it's unique, then what do we have? Go back up here. We know that this is 0 when we plug in theta hat by definition of the MLE for theta. Plugging in theta hat all the way along, we'd have a theta hat right in there. And if this is not 0, then this will be forced to be 0. And yet, if we're finding the MLE with respect to tau, we would take the derivative here with respect to tau, and the solution for tau would be the MLE for tau. So what I'm saying is this. I'm saying the derivative with respect to tau of the new likelihood, if we plug in theta, is 0, and that comes from assuming that the left-hand side was 0, and also the derivative with respect to tau of L tilde of tau of theta, like all hat, or at least the hat over the tau, is 0 by definition of the MLE for tau of theta. And if you assume that there's only one 0 and that you actually found a maximum, then this is going to imply things are nice, that that tau of theta hat must equal tau of theta all hat, assuming assuming that there's only one, there's a unique maximum here, and there isn't a minimum. That make any sense? And I do have, sorry. No, go ahead.
Looks like you might be able to do this. Like, it might be harder, but if you said something like the tau is continuous and either strictly increasing or strictly decreasing.
Yeah.
More general. And I feel like we could definitely get counterexamples if we violated either of those two things.
don't think we need. I don't think we don't need it to be strictly increasing or strictly decreasing. This would work if like tau of theta was, say, oh, I'm worried about this condition. Yeah, this proof does not work unless it's strictly increasing or strictly decreasing. But you could have tau of theta equals like a sine of theta. And I will type up this proof. We can show that this holds, although it does not follow from my proof. So in my proof, we do need tau strictly increasing or strictly decreasing. But we can have things that are not invertible or necessarily increasing or decreasing. I claim. I haven't convinced you yet.
I have a two questions.
Yeah.
So the first question is, does this invariance property hold for multiple parameters? Like a multivariate
Yeah, it does. And we're getting closer to the list of great properties of MLEs that we want to prove, like a maximum exists and is unique under what conditions and all of that stuff. But this does hold for multiple parameters.
Okay. And then my second question is, so the only condition on tau is that the derivative is non-zero across the whole. Or,
No, that's the condition for this proof, because the sine of theta will have zeros, when it reaches the top and bottom, and yet that's still okay. So I need to write this up more generally and convince you of this. I'm going to try to type it up tonight or tomorrow, and if I don't, because sometimes I'm really behind on these things, you need homework 5 back, which is coming back today, then I will start the next lecture with this, which is something I don't want to do, which will force me to type it up.
okay.
Okay.
Could just make it a homework assignment.
Yeah, I wouldn't do that. Well, no. Other questions that I'm not going to answer? All right. All right, cool. MLEs are nice for a lot of reasons. I have to put some conditions on our underlying PDF in order to say that an MLE exists and that it's unique, and that it has all the other nice properties I've talked about, like asymptotic unbiasedness, which means that if we have an MLE for theta, it's a function of n. I usually don't write that sub n. And it's not necessarily true that the expected value is theta, but it is true for almost all MLEs that the limit as n goes to infinity is theta. I'll write that down eventually in a nice list, not a scrawly marginal note. But in order to prove this and all the things in the list that I haven't listed yet, we need to talk about the Cramér-Rao lower bound. I love this thing. I mean, it's no umvu, but it's really fun to compute Cramér-Rao lower bounds. So it's going to look like, kind of like we just forgot about MLEs for a moment. Well, we do it for more than a moment. For the rest of today and probably the first half of Wednesday, we're not going to be talking about MLEs, but we need this thing called the Cramér-Rao lower bound to get nice properties of MLEs. So bear with me, if you will. For some reason, we're talking about the Cramér-Rao lower bound, which is always called the CRLB in MathStat acronym land. And so again, I want to put like if I was in class, I would be putting a squiggly line on the board. That's usually one of my thought breaks. Like, we're going to talk about something completely different for a while. Okay, so here is the setup. And this is the setup for a one-dimensional theta. And 5520, they don't get anything more than that, but you guys are going to get higher dimensional thetas. But I just want to start with the one-dimensional theta. So for a one-dimensional theta. I'm going to put some, I guess, bullets here. So consider, so we have x1 through xn, and they don't have to be IID. They just have to have some joint PDF f of a vector x and theta. They're depending on theta, and I'm assuming theta is one-dimensional. So consider estimating maybe theta or maybe tau of theta. I'm going to let t, capital T, it's a statistic, which is going to be like a little whatever. That's supposed to be like early lowercase t, because I like to save, this is how I make a lowercase t. I like to save that for when I actually put the numbers in and not the data. But I don't think I'll have to write that even more than once, so it's not that important. But I'm going to let this be any unbiased estimator of tau of theta. Then here is the punchline. So under certain regularity conditions, which we will uncover as we prove this, we're gonna, rather than prove the conditions, I'm gonna go through the proof and say, well, if we could do this, then we could say this, and we'll figure out what those conditions are. And they are conditions. So when you see regularity conditions, it's really a more mathy way to say that things are nice. So under certain regularity conditions that we will explicitly write out, we have that the variance of the estimator t must be greater than or equal to, I'm gonna write it, we don't have notation yet, so tau prime of theta squared over the expected value of the derivative with respect to theta of the joint PDF. Now, if there's nothing random, this expectation doesn't make sense. So this is the joint PDF with the capital X's plugged in. That is wrong. I need a log in there between the derivative and the PDF. The derivative of the log of the joint PDF with the capital X's plugged in, otherwise there's nothing random. And then this whole thing, including the derivative, gets squared. What we've written down is a lower bound for the variance of any unbiased estimator for tau. So this thing on the right here is called the Cramér-Rao lower bound for tau of theta. And that's what people say, but that is really misleading. And I'm going to say it as well, but this is misleading because it's not bounding tau of theta in any sense. It is a lower bound on the variance of all possible unbiased estimators of tau of theta. If you had x1 through xn IID from a distribution that depends on some theta, if you can find an unbiased estimator whose variance actually attains or is equal to this Cramér-Rao lower bound, you necessarily have an UMVU. Unfortunately, this is not always a sharp lower bound. It may be lower than the lowest one. So that's not how you really find an UMVU. But I'm out of time. Thank you, and I will see you next time.